Now that we covered the core data structures in a file system, it is crucial to ask how the file system stores and reads files. That is, what is the flow of operations that the file system takes to maybe write to a file or create a new file or like read a file into the memory. Let's, for example, assume we have a file bar inside foo, which is already inside the root directory /. And let's say bar has 3 blocks and its inode number is 99. So the thing is that the file system must know or figure out that bar is mapped to the inode number 99, right? It cannot magically know beforehand. So what is the process that the file system takes to first find the inode that is representing, at the low level, the file we're looking for? And this is where traversing comes into play, So, as you know, in Unix file systems, or Unix-based file systems, we have like a strict and rigid structure of path names, right? We start with a slash, that is in an absolute path, that is, and we start with a slash. Then we, in each section, which is again separated by more slashes, we specify the name for the directory and perhaps the file at the end. And so, like, the important thing to know is that the root inode / is actually a well-known inode number, right? So the file system knows that it always has to start with inode number 2, for example, which is the root inode, to traverse the path to reach the desired file or, let's say, directory. And it could be a global variable or it could be within the superblock. It depends on how you implement your file system. It doesn't really matter. But the core thing to understand is that the file system always knows the root inode number so that it can start traversing through. And the traversal operation is a recursive operation or an iterative operation. Again, it depends on how you implement. And so we go through the inode, we basically look its directory entries, and we find foo is mapped to inode number 42. We already discussed in the previous video that in directories we have basically a pair of the directory of file name and its inode number. So we find that inode 42 is actually the inode for foo, and we again do the same thing for foo. We find within its directory entries that there is a file named bar with inode number 99, and this is basically how the file system finds the inode representative of the file bar. So let's see how we actually read a file from the disk now that we know how a traversal happens, right? So this diagram, like, we'll go through this and then we'll just figure it out as we go on. So as we go downwards, the time increases in this diagram, and here we have the system calls, and here we have basically the disk operation, so reading from the disk to the memory or writing to the disk. And so let's see. In the first phase, we actually do the traversal operation. We read the root inode, then go through its data blocks, or let's say we find its data blocks to go through its directory entries to find and look up foo's inode, right? And again, here we do a repetition of the same process. We read its data blocks, go through its directory entries, and we find bar's basically inode number and read the inode data into our memory. So here now we have access to bar inode, or let's say bar's inode data, and we need to actually now read the data blocks into memory. As we said in our example, we have 3 data blocks. Assuming we have, let's say, assuming each data block is 4 kilobytes, we have 12 kilobytes of data in total, right? So first we actually read the bar inode and find the pointers, let's say the first direct pointer to the first data block, and we read the data itself into memory. And at last, in this final part, we actually do a write operation. Why? This is to update the metadata. For example, we update the last access time within the bar inode, right? And the next 2 read operations does the exact same process. The only difference is we find the second direct pointer and read the second data block, and then in the third read operation we bring in the third data block into our memory. After this, we will have, you know, the all of the 12 kilobytes within our memory, and we could like do whatever we want with it in our program. Let's now go through writing to a file. So the principles are more or less similar. We do traversal, and we have to like read and write to inodes and data blocks, you know, update metadata and such. But the complexity that writing to a file has is that we need to, or we may have to, allocate new blocks. If, for example, we want to create a new file, or if we are editing a file, but let's say the last data block's capacity is surpassed, we have to, you know, still allocate new blocks for the file we are editing. And because of that, we might have to handle some extra cases. Again, here we will go through a similar diagram. Let's assume we want to create a file bar within the subdirectory foo, which is within the root directory. We can see that, again, we do a similar process as reading. We have to first traverse and find the foo inode. We do that, so we go read the root inode, then its data blocks, go through its directory entries, then read its the foo's like we read foo's inode and its data blocks. Here we would probably check if bar already exists or not. And when we confirm that it does not, we need to actually, now the difference here starts. We need to go through the inode bitmap to find an empty inode. Let's say inode 99 is empty and set to 0. So we read it, then we set it to 1, meaning that we now want to allocate it to a new block or a new inode. And we update the directory entry here, and let's say we map bar to, let's say, inode 99 now. And the bar inode is now initialized. We read it to memory, let's say set some metadata and initialize it to whatever we want. And finally we have to update the foo inode to, you know, accommodate the new inode allocation for bar. And after this phase, we have to actually go and read again the bar inode to bring it into memory. Now after that, we need to start allocating data blocks, because we have 3 blocks that we want to write to disk, and for each block we need to find an empty one. Let's say we find data block 112 to be empty. So again, we read it to memory, we set it to 1, and then we have to actually go and write the data within that data block 112. And we update the bar inode to, you know, update its metadata, but also we need to update its pointers, let's say the direct pointer, the first direct pointer, to point to this data block that we just allocated. Second and third write operations does the exact same thing. The difference is that, let's say if it's data block 113, we need to allocate our second data block to that, and the third data block for bar is basically written to this. And after this, we are basically finished writing, or let's say creating, the file bar. So let's go through some key takeaways and notes before we actually end the video. The first thing you might have noticed is that the amount of I/O operations is directly proportional to the length of the path name, right? So the longer the path name, the longer the traversal operations, and as a result of that, the number of I/O operations. The second thing is that both reading and writing can have higher I/O costs, right? And like, there are different strategies to handle this, but the first thing that comes to mind, and is very important, is caching, which, you know, we can cover that in a different video. And the second one is the allocation strategies, which also is related to caching as well. So if you allocate, let's say, contiguous blocks, in our example we had bar, which had 3 blocks. If we allocate it to data blocks 112, 113 and 114, which are like next to one another, we are minimizing the cost of, you know, each reading and writing, because, you know, the, let's say the disk's head will have a short amount of time moving around. But if it's like not contiguous, it's fragmented, it's going to take much more, especially with, you know, larger files, to do these operations. So, you know, just keep that in mind. Later we will come back to these concepts, and we will have a better understanding of how we can minimize I/O costs in file systems.